It's a great pleasure for me to welcome you to the first ever Department of Statistics public lecture talk. My name is Murli Haran. I'm professor and head of the Department of Statistics. The idea behind this public lecture series is for us to share some of the wonderful work that happens in the Department of Statistics with a broader audience, as well as provide some of the insights that we as statisticians have about many of the interesting and challenging problems that face the world today. So that I'd like to really kick this off by providing an introduction for our speaker. It's really wonderful to have as the very first speaker of the series, Dave Hunter. Dave has done an immense amount of highly influential research in statistics, in particular in three areas, in MM algorithms, network models, and mixture models. In addition to doing world-renowned and influential research, he's also a dedicated teacher and has contributed immensely through his service to the department, the university, and the profession. So it's really a pleasure to have him as our very first speaker in the series. Before we begin his talk, I just wanted to note that we will have two moderators today. At the end of the talk, we will have an extended question and answer session led by Kyle Stanley and Olivia Beck, two of our PhD students. And there's some information up on the screen in a second about how you can relay those questions to them. They will act as moderators and ask the questions on your behalf. And if you're not quick enough to quickly snap a photo of this, use your phone on this, or to get the information on the number, don't worry, we'll put this back up at the end of the talk. We should have an extended period of time at the end for you to have all your questions answered. So with that, please join me in welcoming Dave Hunter.
We'll let you know.
Okay. Right. So yeah, this is true. My statistical consulting project was declared unconstitutional. More on that later. This is not going to be a very technical talk. In fact, if it turns out that it's too technical, then I've failed somehow. So let's see how we do. Right. It's not that I can't get enough of this particular picture, and that we've seen it so much in the last 15 minutes. But there's a reason that Mike Fleck took this picture. So first of all, thank you, Mike. And Mike is this poor guy who's running around trying to make all the technology work in the back there. Mike also took this picture. And the reason that we specifically went out to this site, which I'm sure anybody from Penn State will recognize, to take the picture was because we wanted to harken back to another photograph that I'm going to kick off the talk with. Right, so for those of you who are not Penn State people, what you're staring at in the background of this photo is Old Main, which is the main administrative building on Penn State's campus. And so this is a 2022 photo. I'm going to take you back to the mid-1970s, and we'll see how we do. We'll try this transition here. See how well it matches up. Okay, so there's a few more trees and bushes in front of Old Main in the mid-1970s. You can tell that there's something else going on here at the bottom of the screen. There are some people there that look like they're cut off, and that's kind of our jumping off point. So let me show you what the rest of this picture looks like. This comes from a paper called Living Histograms. So Brian Joyner, it turns out, was a faculty member at Penn State in the 70s. He's incidentally one of the three co-founders of Minitab, the statistical software company. Minitab is a Penn State product. It was originally founded by three Penn State statistics faculty members, one of whom was Brian Joyner. And right now what you're looking at is Brian Joyner's intro stats class, whom he paraded out onto the Old Main lawn to photograph in this very particular way. And it's kind of hard to tell what's happening here. I'm going to zoom in for you a little bit so you can see this is an excerpt from the photograph. If you stare at this, what you see is that they're holding some signs here in the front. These are heights. So you can see this is 5'6", this is 5'8". So every student here is lined up according to their height. And what we see in the picture is the shape of the height distribution. What I'm going to do is use this as an instance of what's called unsupervised clustering. And so what I'm going to do is take these data, this picture in other words, and ignore any information that I might be able to glean from the photograph itself in terms of who's a male and who's a female, right? So this is what I'm talking about. I'm going to ignore the male and female cues. Of course, we could do that to a certain extent, but there would be some people that we really couldn't identify here, so this is not entirely a crazy thing to do. The fact that I'm ignoring all of the gender information over here is what makes this an unsupervised clustering problem. So let's talk about what that is all about. In unsupervised clustering, or clustering generally, according to Wikipedia, we're dealing with the task of grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. Now, I can tell you, I'll give it away the punchline here. I'm going to take issue with this definition of clustering. It works for some types of clustering, but this is the definition that's used by most of the world for all of clustering. And I think that in a statistical context, it helps to think of clustering in a slightly different way, and we'll get to that later. So basically the question now is, in an unsupervised context where I don't have any gender information, can we still back out males and females somehow from these data alone? We're going to use statistical distributions to try to do this, and if you think that this answer is no, you're right. We can't possibly take somebody who's, 64 inches tall and say that's a woman or that that's a man, right? That's too much to ask. So what is it that we're trying to get at? Well, here's a solution to the question of clustering as I would view it. You'll notice I've also inserted a modifier here. So in a statistical context, when we're dealing with clustering, or unsupervised clustering in particular, I'm talking about model-based clustering. And so what we're going to do is impose a model here. What I mean by that is we're going to assume that the males and the females both follow what's called a normal distribution. That's a bell-shaped curve. You're seeing two of them on the screen here, right? So the one on the left is clearly the women, and the one on the right is clearly the men, and the dotted black line here is the sum of the two. And so somehow we have a population that's comprised of both males and females. Together, they give us this sort of dotted black line, and our question is, can we discover the blue curve and the red curve? The answer is yes. This is kind of an easy statistical problem. How we do that is we rely on the fact that any normal distribution can be described by two numbers. Its mean, which is this Greek letter mu, and its variance, which is this sigma squared, right? So as long as I know those two numbers, then I know everything there is to know about a normal curve. And so for instance, this blue curve, all I need is two numbers. I need to know the mean height for women, and I need to know the variance. The standard deviation, which you may have heard of, is the square root of the variance. So variance and standard deviation are interchangeable in a sense. So this is our model. Right? So what I'm saying here is that we have two normal distributions. That's what the capital N's stand for, N for normal. Each normal has a mean. In the left case, it's mu sub f. That's the mean for females. And we have a variance for females, sigma squared sub f. For the males over here, we've got mu sub m and sigma squared sub m. And then we also have lambda. Lambda is the proportion of women, the proportion of females. And of course, that means that 1 minus lambda is the proportion of males. Right? So this is our statistical model. Now, back to Wikipedia. Clustering is the task of grouping a set of objects. I would say no, that's not necessarily what clustering is. And in this case, we're going to define clustering slightly differently. Rather than focusing on the objects, we're going to be focusing on the groups, right? So clustering in a statistical context, I would claim, is about describing the groups. Sometimes you'll hear the word learning used. So what we're trying to do here is learn the model. By which I mean figure out what these Greek letters stand for in terms of numbers. So how does that work? Well, I'll tell you more about that in a sec, but this is just too interesting. It turns out that even though it looks from our histogram as though what we're talking about is a two-humped distribution or bimodal distribution, right? The dotted black line certainly goes up and down and up. The question of whether human height is bimodal is kind of an interesting question. There is, in fact, a paper in a really well-known journal called the American Statistician, whose title is human height bimodal, question mark? And the essential answer is no. Right? So what these folks did was they actually took data from the CDC on males and females, their mean heights and their variances of heights. And if you combine in the sense that I was doing on the previous slide, you actually don't get a bimodal distribution. But I digress. Back to our story, right? So we're back to trying to do model-based clustering, which is unsupervised clustering, and estimating the parameters in our model here. Now, you may have noticed that the sigma squares have turned black here. They've lost their subscripts. I'm actually going to impose that as a condition. I'm going to assume that the males and the females have exactly the same standard deviation, i.e. variance. And so I don't need to write an F over here and an M over here. I'm just going to make one sigma squared. The reason I'm doing this is for technical reasons that we're not going to get into in the talk. But this is our model. Now, what this model does is it tells us how we would expect randomly drawn individuals to behave. If this is our model, and we said, well, let's just pick somebody at random from that model, the probability distribution that I've written down tells me what I can expect of that person. And one of my very favorite quotations about statistics is that statistics is probability in reverse. This both captures what it is that we do as statisticians and also explains why it's necessary to study probability in order to do statistics well. So if this is our probability model that explains how data would behave, we're actually going to start at the other end. We're going to take our data and see what we can learn about the parameters here. That's the sense in which statistics is probability in reverse, right? So what we're going to be about today is starting with our gray lines, sort of ignoring the solution that's being presented to you, right? That's what we're trying to find, and using what I'm going to call an EM algorithm to try to figure out what our best estimates of these parameters are. That's what statistics is all about. They are going to be called maximum likelihood estimates. If that's something that you've come across, that's what we're about to discover. And we're going to be doing that using an EM algorithm. EM stands for expectation maximization. And it's a really technical thing, right? There's a lot written about the theory of EMs, but in the case that we're considering, it turns out that there's a really intuitive feel to the EM algorithm, which is why I'm going to show it to you how it works. So the first thing that we do in an EM algorithm is we just start with some random values. We don't really need to know what these are. We can just pick anything we want. And you can see I've chosen the mean for females as 63 inches, for males as 67, right? You can sort of line those up. I've also chosen a proportion of 1/2 exactly for females. And you can see that these scaled heights are now exactly the same height. I've also chosen a standard deviation of 2, which means the variance is 4, right? So I just sort of arbitrarily wrote these normal curves on top of my histogram. The next thing I'm going to do is I'm going to assign each individual probabilistically. So, for instance, if I look at the 65-inch people, I'm choosing 65 because that 65 happens to be exactly the point at which these two curves cross. And so to assign somebody probabilistically as, let's say, a female, what I'm going to do is take their height, 65, look at the height of the blue above that, right? And then I'm going to compare that with the height of the red. And the way that I'm going to assign this person probabilistically as a female is I'm going to take the blue height, divide it by the sum of the red and the blue. And so for the 65-inch folks, because the red and the blue heights are identical, I get 1/2 as my ratio. So everybody in this bin here in my histogram will get 1/2 score towards the female side and 1/2 score toward the male side. So that's what I mean here. The next thing I'm going to do, now that I actually have a whole bunch of people that have been assigned fractionally as females, I can do things like finding a mean, finding a variance. Then I'm going to do that. I'm going to use those new variances and means and come back up here and repeat, okay? This assignment, this probabilistic assignment is called the E-step. This re-estimation of parameters is called the M-step, and that's why it's called the EM algorithm. So we're going to see how this works. I'm going to take these starting values, and this is what they look like in an E-step. This is what it looks like when I do that probabilistic assignment. And in particular, you'll notice, for instance, that the 65 bar is exactly half full of blue. Right? That's because everybody in the 65 bar gets assigned a probability of being female of 1/2. Obviously, the folks to the left, which are more where the blue height is much higher than the red, have a probability greater than 1/2. The folks to the right have a probability less than 1/2, to the point where basically over here there's 0 probability, according to our original red and blue, that you are a female. Now I can take the blue mass and get a mean and a variance from it. I can also calculate a total proportion. Those are the next parameters that I plug in here. This proportion 0.328 comes from the or what fraction of this whole histogram is shaded blue. Here's my new mean, here's my new variance, and I'm going to do the same thing for the unshaded portions because that's the male side. I'm now going to take these new parameters and go back and do the e-step again. Right? So in every slide that I'm about to show you, the m-step parameters will be what you plug in on the e-step for the next step, or for the e-step at the next iteration, right? And this eventually leads us to our solution. By about iteration 15, things aren't changing very much. I'll skip ahead 5 at a time now. Here's 20, 25. Things are really slowing down. By the time you get to the 35th iteration, we're at a solution. Things have stopped moving. And this is how we find a maximum likelihood estimator using an EM algorithm for what I claim is a fairly simple problem of unsupervised clustering. Right? So just to summarize, we found these parameters based on nothing more than the set of heights that we were given, ignoring entirely any cues about male-female. And what we did was really not cluster people, right? We didn't take a 67-inch tall person and say that's a male or a female. What we did was we tried to learn about the clusters, not the objects. And that's a theme that I'm going to carry forward into the next example, right? So I'm going to now shift from unsupervised clustering into supervised clustering, but this theme will carry forward. So the unsupervised, the supervised clustering project. So now we go back to my grad student days. So this is where I spent a lot of time as a graduate student. This is the Rackham building on the campus of the University of Michigan. I worked in the CSCAR, the Center for Statistical Consultation and Research, and somehow I just wound up with this particular client's problem. I'm not really sure why the director assigned this to me, given that it turned out to be kind of an important problem, as we're about to see. But the question from the client was this: how can we revamp the undergraduate admissions at the university so that it could survive a court challenge? There's more to the story than that, obviously, so let me tell you a little bit about the history here. Now, I'm not a lawyer, but I will try to play one on TV. So going back to 1978, there was a Supreme Court decision called Regents of the University of California v. Bakke. Bakke was a gentleman who had applied to the medical school at UC Davis and was admitted twice. Was rejected twice, otherwise he wouldn't have sued. He was rejected twice by the med school at UC Davis. And at the time at Davis, they had a system whereby I believe it was 100 slots were available to the incoming med school class. And Davis set aside, I can't remember, was it 25 of them? 25 for particular sets of applicants, right? They were trying to diversify their med school population, and so they basically said, we're going to hold out a certain number, a certain percentage of our slots for folks from certain groups. Bakke sued. He said that that was not constitutional under the 14th Amendment, and it turns out that the Supreme Court agreed with him. So the Supreme Court said, yeah, UC Davis, you have to admit Bakke. And in doing so, they laid out some legal, precedent. Precedent is a weird word to be using in 2022, but more on that later. So here's what happened. 4 of the justices held that the use of race as a criterion in admissions decisions was constitutionally permissible. Justice Powell joined that opinion as well. So this, basically the majority was saying that the use of race as a criterion in admissions is okay. All right, how? Now let's fast forward to 1996. So Hopwood v. Texas. And by the way, the reason that I'm showing you this, I'll tell you why the map is up there later. So Hopwood v. Texas in 96. Hopwood sues the University of Texas with the help of an institution called the Center for Individual Rights, who figures prominently in our story, even though I didn't put them on the slide. Hopwood was rejected from the law school at the University of Texas, and in deciding this case, the appellate court of the Fifth Circuit basically cited the Bakke decision, right? So under Powell's conception, a host of factors that include race would be constitutional, but what a school could not do was to refuse to compare applicants of different races. So in other words, it's not okay to have 2 parallel systems, one for one group and one for another group. It's okay to have things combined, though. You can have race as one factor among many. On the other hand, the Fifth Circuit says, nope, we reject that, and basically says the use of race per se is proscribed. This means that henceforth, the UT is not allowed to use race in its admissions at all. In fact, this was valid for the entire Fifth Circuit. The Supreme Court did not review this case, and so the Fifth Circuit's decision held. Now, Michigan. You might remember that this was 96 when I was approached about this question. So at the time of the Hopwood decision, Michigan was using distinct admissions criteria. They basically had two systems, and one was for one group, basically, and one was for another group. And the two groups that they were most concerned about were URM and non-URM. So URM stands for underrepresented minority. And in my understanding of the previous system at U of M, again, you sort of, if you were in the U of M camp, you sort of had this set of criteria over here, and if you were not, then you had this set of criteria over here. They felt that this would be seen as not constitutionally defensible. And so they would like to, what they wanted to see was one system that combined race as one factor among many, right? So that was the goal. Why did they think that this might come up? Well, because it turns out that the Fifth Circuit was not just sort of arbitrarily, popping up as the place, as the venue for that court challenge. CIR was very strategic. They chose the Fifth Circuit because it was a very conservative circuit. The Sixth Circuit, where Michigan lies, is also considered to be quite a conservative circuit, and this is why Michigan was suspicious that they might possibly be sued coming up, right? So that's why they approached the CSCAR, and that's why I ended up trying to figure out a system that included race as one factor among many. The data that they provided for me were a set of admissions decisions. There were 800 applications. And by the way, I just need to say right now, everything that I'm about to say is from memory. All of the stuff that I worked on, I had to turn over as whatever, like attorney work product or something like that. I was not allowed to talk about the case, blah, blah, blah. Nobody ever told me it was okay to talk about it, but I figure since it's actually now past the Supreme Court phase, I'm safe. But I don't have any of the stuff. I would love to see some of the materials that I used while I was working on this, but I had to turn it all over and I didn't keep any copies. I don't know whether that was a good idea or not. But at any rate, what I do remember is that I had a data set consisting of 800 students who had applied to U of M. We stratified this sample, so in-state, out-of-state, they knew that that was an important variable. They also knew that URM student or not, that was an important variable. So basically what I asked them for was 200, 200, 200, 200, right? So just to make sure that we had nice representation in all possible combinations of these two variables. And this is the sort of thing that I would say now, I tell you, these are not the actual races. So first of all, you would know that because I, of course, did not use Python on a Jupyter notebook in 1996, right? Anybody who knows that will know that that could not possibly have happened. So these are not the actual data. I don't know the actual data. I don't have them any longer. But this is the sort of thing that you saw. First of all, this column over here is whether or not they were admitted, and then we see a whole host of other factors for a particular applicant to the U of M, including, here we are, U of M student, which is true or false, in-state, which is true or false. There are other things that I remember distinctly, like child of an alum, that came in there, class rank, I'm trying to remember what else. Anyway, most of what I'm talking about now is from memory, so I'll do my best. What I used was, I guess, what would be considered a very rudimentary method by today's standards called logistic regression. And part of what I'm going to try to argue today is that it was a good thing that I did. Lost the court case, but it enabled some debate that I think is healthy. So logistic regression, good, if simple. What does logistic regression do? All right, so the input here is a linear function of the predictors. Now, by predictors, I mean everything other than the admit column, right? So predictors include all of this other information. Now, what you've got here, if you're familiar with regression, you've got your beta parameters. Each one of these betas multiplies one of the predictors. The thing that might be, so GPA, I think that's pretty obvious. Beta 1 times GPA. The GPA, you just take the number here. This one might be a little bit mysterious. Capital I stands for indicator. So capital I sub SAT greater than 200 means it's either 0 or 1. It's the indicator that the SAT was greater than 1200. So you either get a 0 or 1 depending upon whether, and it turned out that using SAT as a numeric score did not work as well. If I remember correctly, basically there was a certain threshold beyond which, as long as you surpass that threshold, it seems as though Michigan gave you all of the weight toward getting in that you were ever going to get from your SAT. So, and that was 1200. So once you got above 1200, there was not very much that you could improve your chances by SAT scores. And so that's why we ended up using SAT not as a numerical variable, but rather as a set of indicator functions. And then over here at the end, you see there's a beta that multiplies the indicator for URM status. Okay, now the output. Well, if you think about it, what we're trying to predict is these guys here. And by the way, this is what supervised clustering is all about. It's supervised because I know what the answers are supposed to be. So I'm actually, when I'm learning the model, I'm trying to figure out what the betas are that give me these. The problem, though, if you think about it, is that everything over here could just be numbers, real numbers. In fact, they could even be negative. And how is that going to give us trues and falses? Well, the way that logistic regression works is that we model this function of the probability of admission. And if you think about that, you realize probabilities are between 0 and 1, and I just got through saying that these things can be anything, including negative numbers. They can be bigger than 1. And so we can't just put probability over here by itself. We need to transform the probability. If you're interested, the transformation is actually the inverse of the logistic function, and that's why it's called logistic regression. But let's get into how the data can help us learn this, right? So the first thing we do is we look at, student number, well, I guess it's 0 here. This is another Python joke. Student 0 has a bunch of information here, and we just plug them in, right? We plug in the numbers for GPA. Here's the indicator of greater than 1200. Here's the indicator for greater than 1300. Here's the indicator for URM. Again, these indicators are either 0 or 1. And then somehow we need that to predict that it was an admit. Right? We just go down the list and we plug in all the data and we get all of our, setting up of the logistic regression problem. I'm not going to talk about how logistic regression works. It is another instance of maximum likelihood estimation if you're interested. But somehow we need to learn these betas and learn the model. Okay, so here's what we get. It turns out, that was supposed to be all in one line. That's all right. So these are the betas that we didn't know. Here, turns out, are our best estimates. Again, this is completely fabricated data, but I just want to give you a sense. And there's some dots in here. If you're trying quickly to do the math, it doesn't work out because I knew that there were some dots here. So the things on the left don't quite add up to the things on the right. However, a couple of things that you notice. The things over here that were supposed to turn out false are negative. The things that were supposed to turn out true are positive. And it turns out that what that inverse logistic regression function does is it takes a probability that's less than a half and turns it into a negative value. And it takes a probability that's more than a half and turns it into a positive value. So essentially what you want to see is positives match up with things that we observe to be true, negatives match up with things that we observe to be false. So that's a good thing. Now, we can't do it perfectly, by the way. There are simply too many, there are too many observations and too few parameters, basically, to get it perfect. All right, so this is terrible. This is not very helpful if you're trying to design a system that the University of Michigan admissions office is supposed to be able to use. And so we would like to clean this up a little bit to change them to nicer numbers. So the first thing we do is we get rid of the 9.12 because it doesn't matter, right? The only thing we want to know is who's higher and who's lower. Right? So shifting by a negative 9.12 is totally irrelevant, right? Because that doesn't change the relative ordering of any of the students. So we can just get rid of that 9.2 entirely, right? So now we have a bunch of numbers that are all positive over here on the left. Fantastic. Again, the higher numbers are the students who are more likely to be admitted, and conversely. And so just to clean this up a little bit more, let's now just multiply everything by 10 and round, and then we get some nice numbers, and here we go. And these numbers are actually the correct numbers as far as I can recall. For instance, GPA gets 20 points as that multiplier. And the reason that I know that's correct is because it's written in the Supreme Court decision. Same with the SAT, right? So SAT has a total of 12 points possible, but I'm nearly certain that it was 10 points if you were at 1200 at least. And then you could get maybe 1 or 2 extra points if you were like above 13 and 1400. I don't remember exactly how that works. Importantly, over here in the URM indicator, the multiplier is 20, okay? So that's where we are. What I can recall is that students who scored greater than 100 in my data set always were admits. Students who scored less than 90 were never admits. right? So it seems like you want to put the threshold, right? If you have to communicate to the admissions department that this is your formula and your cutoff is blah, well, the blah should be somewhere between 90 and 100, right? It turns out that there's a small misclassification rate. It didn't matter where we put the cutoff, right? So again, there was no way to do this perfectly. That's typical, though, for a logistic regression problem. In fact, it's almost problematic if you don't have this problem to a certain extent in logistic regression. I don't remember what the correct decision rate was, but I know that it was around 95%. I think it was in the like maybe 96, 97% range. This would be considered not good by modern standards, right? So a lot of what modern research on supervised learning does is try to pump up this number as much as humanly possible. And I'm going to argue that that is not necessarily a good thing. It might be a good thing in some contexts. I think it's not necessarily a good thing across the board. So this formula basically helps the admissions department focus on borderline cases. It can be adjusted, right? So one thing I remember well was when I was talking to them about this, I said, look, if these numbers don't jibe with what you guys think is important, then just change it, right? Because you're the admissions experts. All I did was try to reproduce past admissions decisions based on the data that you gave me. I don't know anything about admissions, right? I'm just the statistician who tried to come up with this scoring system for you. I don't think they changed anything at all, as it turns out, because a lot of the same numbers that are in the Supreme Court decision jibe with what I remember. So anyway, it can be adjusted even if it's not, and now it makes explicit what had previously been implicit. Okay, and this is an important part of what I'm going to be arguing. First of all, statistical models, once again, help us understand, not just predict. And right, this is sort of hearkening back to the theme from earlier, right? It's not just about classifying individuals for the future as admits or not. It's also about understanding why, how. Okay. Yeah, they were sued. And the timeline was sort of like this. There was a woman named Jennifer Gratz who was denied admission to UMich. By the way, just sort of interesting side note, I gave a talk about this in April at the University of Michigan. It was great to go back to Michigan and give this talk. There was a guy in the audience who's the husband of a former colleague of mine who had her in class, who had Jennifer Gratz. So basically she was denied at U of M. She went to U of M Dearborn, and he's a math teacher at U of M Dearborn. He said, yeah, she was in my class. So anyway, I thought that was crazy. So Gratz and Hammaker, I'm blanking on his name. She's the famous one because her name is in the Supreme Court title. So two students filed a class action lawsuit. 99 was the first year that UMich rolled out this new system that I helped develop. And when this made it to federal district court, basically it was a split ruling. What the federal court essentially said was that now that Michigan has changed its system, it's okay. So basically Jennifer Gratz and the other plaintiff won their cases because they were admitted under the previous system, which wasn't constitutional. But the federal court felt like now that Michigan has a system that treats race as one factor among many, no problem, right? So it was kind of a split ruling in 2000. Of course, the whole point of this was not to get these two admitted. It was to challenge the whole system to begin with, right? So it was appealed and eventually made it to the Supreme Court. And in the Supreme Court decision, actually there were two of them. So Gratz v. Bollinger is the one that I was involved with, right? Because Jennifer Gratz was an undergrad applicant. There was also a second case called Grutter v. Bollinger. By the way, Bollinger was the president, Lee Bollinger was the president of Michigan at the time. So that's the Bollinger and Gratz v. Bollinger and Grutter v. Bollinger. This was an applicant to the law school. And so these two cases went up to the Supreme Court at the same time. And they were decided in 2003. And so the question before the court, I love oye.org. Again, I'm not a lawyer, but this is kind of fun to read. Did the University of Michigan's use of racial preferences in undergraduate admissions violate the Equal Protection Clause of the 14th Amendment and Title VI of the Civil Rights Act of 1964? Yes, the Supreme Court says, by a 6-3 majority. Because the policy did not provide individual consideration, but rather resulted in the admission of nearly every applicant of underrepresented status, of URM status, it was not narrowly tailored in the manner required by previous jurisprudence on the issue, i.e. the Bakke decision. Okay, so I want to talk a little bit about this. We're getting towards the end of the talk. I want to just sort of cover some of the specifics of the case because I think these are important details. So they're not expected to read this. I'm going to highlight. So this is the syllabus. This is basically the thing that precedes the opinions in a Supreme Court decision. This is a summary. And down here, you can see the current guidelines, our selection method under which every applicant from an underrepresented minority, racial or ethnic minority group is automatically awarded 20 points of the 100 needed to guarantee admission. Okay, so once again, Michigan was using that same 100-point cutoff that we had identified earlier. So that's what the court has recognized. And now in the main opinion, this paragraph is important, right? The court has today rejected petitioner's argument that diversity cannot constitute a compelling state interest. Okay? So essentially, they're reaffirming what had happened in the Bakke decision in 1978. It's okay that diversity is something that universities pay attention to. In fact, remember the second case I mentioned, the law school case? This was clearly decided for UMich, and they abrogated the Hopwood v. Texas decision. So Hopwood v. Texas died in 2003. Because Hopwood v. Texas said that you cannot use race, period. They're saying you can use race. However, 20 points is too much. I mean, that's what it boils down to. And this is why I claim that having a system where we not only get to classify individuals in our clustering problem, but also learn really clearly how that clustering works is a good thing. I'm not happy about the outcome, but if I had if I had access to more modern methods at the time, I'm not even sure what that meant in 1998, that might not have been possible. Okay, so just to sort of back, oh, by the way, anybody listen to The Daily? The podcast, The Daily? This was on The Daily yesterday, thanks to my wife for pointing that out. They get it wrong. Adam Liptak is the Supreme Court guy from the New York Times. What he said was that in 2003, the Gratz thing, they rejected the U of M system because it was a quota system. No. The Bakke system was the quota system. The U of M system treated race as one factor among many. They did not reject the U of M system because it was a quota system. They rejected it because 20 points is too much. Right? So it's a much more subtle argument than yes or no, are you using quotas? And I don't know why the Daily got this wrong. I think maybe he was just confused about Bakke or whatever, right? So there's some subtlety here. And in fact, I mean, race is okay, right? Anyway, I don't want to digress too much about that. Here is an alternative perspective on AI and black boxes. So a black box refers to a method where we can't really tell what criteria are being used in, let's say, a supervised clustering problem. Well, there are lots of decisions in life that are black boxy, right? So if AI is in any way supposed to mimic real I, then maybe black boxiness is not such a bad thing. And so, while I stand here and argue that black boxes are not necessarily a good thing in the context of things that could potentially have societal importance and wind up in front of the Supreme Court, I think that there are situations in which black boxes are just fine, where the highest possible predictive performance is really what you are after, right? But it's a context thing. It depends on the situation. Okay, so to wrap up, so in a statistical context, first of all, I claim that no matter whether it's supervised or unsupervised, clustering is often better viewed as learning about the clusters, not learning how to assign the objects, right? So it looks more like this thing over here that we saw with the heights, and it is not the Harry Potter sorting hat. That is, who knows, right? I mean, that's kind of the archetypal black box. Nobody knows how the hat decides which of the 4 houses you're supposed to go to. Explainable processes, in fact, can be preferable to accurate assignment. For instance, in the case of gender guessing, if you're looking only at height, that is simply futile. And in cases, I claim, such as the one that wound up before the Supreme Court in 2003, black boxes may not be appropriate in all cases. So, with that, I guess we'll do questions.
All right. Let's see if this, I'm just going to project. Thank you, Professor Hunter, for the talk. You raised some really interesting points about model interpretability, black boxes, and their application at scale. We've had a number of questions come in throughout the talk, and we will take the next 20 minutes or so to touch upon some of them. So Olivia, I'll turn it over to you for the first question.
So, I don't want to go for the mic, it doesn't work. So our first question is, in academia, statisticians often devise new theory or methodology, but are not involved, they're often not involved like directly in their application. And so you, off of your opinion, what responsibility do you think academics have to their application of their work, particularly for work whose models lack interpretability?
Well, so it seems like the questions there sort of shifted from statisticians to researchers, but I think they must have meant, what responsibility do statisticians have?
Yes, I believe so.
Yeah, I think that all of my colleagues would agree that the best statistics always comes out of a really deep dive into the application areas. That said, sometimes you are a statistical consultant. In fact, I draw a distinction between statistical consulting and statistical research with applications. So collaborative statistics versus consulting statistics. Sometimes as a consultant, you simply don't have the luxury of being able to deeply learn about the field that you're studying. But again, I think that, again, most of my colleagues would back me up on this. The best science comes out of real collaborations where statisticians are learning as much as they can about the science of what they're doing.
Okay, our next question is also about accountability. Most WMDs, weapons of math destruction or runaway algorithms, won't make it to the Supreme Court. What other organizations from government, industry, or academia would or should act as WMD watchdogs?
Wow. Who should be a WMD watchdog? So I don't know if that question was a plant or had seen the sort of next slide beyond my discussion slide, but WMDs refers to this book by Kathy O'Neill. Here is an example that you can read at your leisure. Who should be the watchdog? I think that, arguing as a statistician, at the very least, that body needs to include statisticians. I think I might get myself into a little bit of hot water for saying this, but I think that we've seen ample demonstration in the recent past that politicians, if they are the only people at the table, will do a horrible job. And so I think that whoever these watchdogs be, it should really be a broad group of people, including statisticians, but not solely statisticians for sure. Beyond that, I don't even know that it's my purview to weigh in on who should be at the table to decide such things.
Okay, our next question here is, so black boxes are black to the end users, but someone has trained the AI, someone has obviously trained the AI, someone has tested it. So the question is, it's not black to everyone, or is it black to everyone? So does the researchers training the AI know exactly what's happening inside of it?
The researchers training the AI have no earthly idea how it's doing what it's doing. If they're using the most modern, and I use that in quotes, methods, they have no idea what's happening. And I'll give you an example of that. If you Google the, what is the data set where you're looking at handwritten digits? Who can help me? What is that called? The black and white digits data set? What is it? MNIST, thank you, the MNIST data set. Okay, so you can Google MNIST and you can learn how MNIST, which is a problem of looking at handwritten numbers and trying to determine what the actual digits are that they correspond to, can be attacked by using something called a neural network, a deep neural network. Lots of words are used for this. And you can even hear a story about what's happening behind the scenes, right? Like some part of the network is learning about, various parts of the image and various shapes, and then the next layer is putting them all together. That's completely fabricated. They have no idea that it's doing that. So I actually don't agree that most AI folks know what's happening unless the model is so simplistic, like logistic regression, for instance, that you really can just look at it and interpret it. Now, I should also say, in fairness to those researchers, interpretable AI is a huge field of research today. And so, yes, while I claim that most sort of off-the-shelf machine learning algorithms and AI are not directly interpretable, there is a lot of work in this area because everybody recognizes it as a problem.
So our next question is about interpreting the model that you worked on specifically. Does this model mean that historically U of M had been assigning 20 points to URM students since that number is based on past data?
And the short answer is yes. And here I think we get into arguments about whether that's appropriate, how much of that is trying to diversify the class. But one of the things that lots of folks have pointed out in discussing this particular case is that some of the criteria that are ostensibly objective, like SAT scores, are somehow mysteriously predictive of race. And therefore, some of those objective seeming measurements have some bias baked in the opposite direction. So some of the 20 points, I think one could argue, is to compensate for that. And then there's probably some additional dollop that's trying to diversify the class, but it's a little bit hard to tease that out.
So our next question, kind of building off of that. So you mentioned that the GPA points was also 20. And so if the URM points and the GPA points had the same weight, why was the URM points considered problematic and the GPA one wasn't?
Well, I don't know that there's anybody who would argue that GPA is not a factor that should be used in admissions decisions. I would also point out that because GPA is measured on a 4-point scale, that 20 is a little bit misleading. The 20 points in the case of the URM indicator can only go as high as 20, whereas the 20 points when it's multiplied by your GPA can go as high as 80.
This is another question about the court's past. Are you aware of any other cases in the court system that are about algorithms like yours? How do you hope we handle court cases about algorithms like these in the future?
I don't know of any. I think that's a great question. Again, I'm not a lawyer. This just happens to have been something that I did as a graduate student. I don't know. And as far how I hope that these are handled in the future, I just hope that there is sufficient information so that, for instance, Supreme Court justices who are not trained in the clustering algorithms that might come before them can understand what's happening. Right? That's sort of what I'm arguing, is that if the methods enable debate by folks who are not necessarily trained in data science, that's a good thing.
Our next question comes in of what was the motivation for you to use logistic regression, and I'm going to build on top of that of if you were to redo this today with the more modern methods that have all been developed since then, what would you choose today?
What would I choose today? That is such a hard question to answer, and I've asked myself this. So the real reason I used logistic regression is because I knew that in 2022 I'd be giving this talk and I would want to be able to, no, it's because that's what I knew how to do. I mean, I was a grad student in statistics. What would you guys do?
Logistic
Yeah,
regression.
Logistic regression,
yeah.
all right, so there we have it. So maybe I wouldn't do anything different.
I think it's all questions.
Okay, there's one more here, or we have a few more questions. The historical context is appreciated. Can you speak to the status quo/ongoing trials regarding the legality of the explicit use of race in college admissions?
Well, all I can say is watch this space, right? Because the upshot of, well, the Daily yesterday, Tuesday, right, whatever, October 4th, is that this may be one of the most important cases before the Supreme Court in the coming term. So I don't know, but it could be very. I think it's specifically referring to. There's a case from Harvard and there's a case from UNC where the use of any kind of race in admissions decisions is being challenged, and many folks believe that the use of race is going down under this current Supreme Court, despite the precedent of Bakke, by the way. I think this court has demonstrated that precedent is not necessarily something that I may be getting myself into even more hot water by saying that.
Okay, another question about model interpretability.
Yeah.
In your talk, you make an argument for models that successfully describe societal phenomena over those that accurately predict those phenomena. Model interpretability is surely important in applications to many problems, but are there situations in which prediction is paramount and those black box predictors are preferred?
Well, if I'm behind, or not behind the wheel, but in the passenger seat of a Tesla that's driving itself, I would really rather that it get the most accurate prediction possible. Or if I'm crossing the street in front of a Tesla like that, right? I mean, yeah, there are certainly instances where prediction is really all we care about. And if they want to go in and try to interpret how that algorithm is actually recognizing that there's a baby carriage in the street and stop, that's interesting too, but I would much prefer that they make sure that it stops.
So our next question goes back to your original model with having the 20 points assigned to the URM. And essentially the case came down to, right, 20 was too much. Do you think there is a number that wouldn't have been too much or that would not have been rejected? And is there a way to like kind of decide where that line is?
That I have no idea. I really don't know. And you know, you sort of now you're getting into what is the psychology of the justices who decided the course. Maybe some of them were relieved that they, like 20 was so over the top that now they can actually just say what they think and not worry about it. I have no idea. There has been quite a bit of writing about Gratz v. Bollinger. And again, I think this is one of the things that's really great about a system where you can actually see what goes into the model, right? This precise question can be argued by legal scholars and not by people like me who don't know anything about it.
Okay, I think we're going to move to the last question. How has this experience informed your work?
Boy, that's a hard one. How has this experience informed my work? Yeah, I guess I have been, in the last 5-6 years, been a pretty vocal proponent of statistics being included within any conversation about data science. And I can say I'm happy to be in an institution where that was not a hard sell. Not all institutions can say that, although I think that any institutions that have excluded statistics are finding that they are kind of on the wrong side of history at this point. Yeah, so statistics needs to be a part of whatever happens in data science. And as I was helping put together, like programs in data science here, we have a major now. The only major at Penn State that's jointly administered among 3 different colleges is our data sciences major. And I think that that's not only a good thing in terms of who it brings to the table, but also philosophically, it's an important statement about what data science is in 2022. So how has it informed my decision making? I guess once I started to understand that being a statistician at the table talking about data science was important, it occurred to me that this experience in the late 90s was actually relevant.
Okay, great. Thank you, Dave, for the talk.